You didn't want us to do anything else with the top that.
Oh, thank you for asking. So the reason that I left it factored like that was because theoretically, depending on what's in my denominator, I could just get like a single number in my denominator, and then maybe I'd be able to cancel something. In this case, it's not super practical because I don't usually cancel radicals, and I'm getting rid of radicals in the denominator anyway, so we're not going to be able to cancel that. But yes, as your final step, thank you for reminding me, we would then distribute in our numerator. But definitely wait until the final step, because if you distribute first and then it turns out you can cancel something, you have to factor it out again, and that means you have to remember to do that. So that's why I waited until the very, very end, because theoretically, whatever this coefficient is right here, we might be able to cancel with a factor in the denominator. And we'll look at one of those here in a minute. Thank you. So let's do, what do I got here? 6. Oops. I should tell you what we're going to do. Rationalize the denominator. And we'll do 6 times the square root of 3 over 3 times the square root of 2 minus 4. Okay, so what do I need to multiply my denominator by to rationalize here? What do you think, James?
3 square root of 2 plus 4.
Beautiful. And so we need that in the numerator and denominator. And be sure you're putting these parentheses in, even in your original fraction. As I was grading last night, all those corrections you guys turned in before the test, I noticed that sort of as we moved through chapter 5, I was seeing less and less of those parentheses, and there weren't a ton, but it caused a few or enough errors in distributing that I think it's worth mentioning. Like anytime there's addition or subtraction in the numerator or denominator, make sure you're grouping that with parentheses so that you remember to distribute properly. So again, we're going to leave the numerator as it is in case I can cancel a factor later. So we're going to leave this guy factored. I'm sorry, my Bluetooth is lagging today. There we go. 3 root 2 plus 4. And then we'll distribute in the denominator. So I have, why can't I draw a straight line? I have 3 root 2 times 3 root 2. So we'll multiply our coefficients. 3 times 3 is 9. And then square root of 2 times square root of 2 is the square root of 4. And then we have 3 root 2 times 4. So we're just multiplying 4 times our coefficient of 3. So 12 times the square root of 2. And then negative 4 times 3 root 2 is going to be negative 12 root 2. And then negative 4 times positive 4 is going to give me a negative 16. And then, like we wanted, those two middle terms add to 0. So they're gone. If that doesn't happen, you should back up and check what you're multiplying by. So our whole goal here when we do this distributing in the denominator is that those two terms that have radicals in them end up adding to 0, so we don't have a radical anymore. So we have 6 times the square root of 3 times 3 root 2 plus 4 over, well, in the denominator, I have 9 times the square root of 4. So the square root of 4 is 2 times 9 will give me 18 there. So 18 minus 16. So 6 times the square root of 3 times 3 root 2 plus 4 all over 2. And then I see that I have a common factor of 2 that I can cancel, right? That 6 contains a factor of 2. And so this will cancel and become a 3. And the reason I was able to do that is that the only operation outside of parentheses is multiplication, so that numerator is fully factored. So we get 3 times the square root of 3 times 3 square root 2 plus 4. And then that's just over 1 because I canceled my 2. So we don't have to write that denominator. And so now the last thing I'm going to do is distribute. So we get 9 times the square root of 6 plus 12 times the square root of 3. And not only did we rationalize our denominator, but we ended up without even having a fraction, which is even less messy. Does the general process make sense? So this is one of the things that it seems like when people walk out the door, it's really easy to forget how to do. So, but it turns out that all of these are basically the same. As long as you can look back in your notes and remind yourself of the idea of the conjugate, once you get the right thing to multiply by, we're just distributing just like we did yesterday and simplifying from there. So let's do one more that's a little bit different. And then we'll solve some equations. So in this one, I'm going to rationalize the numerator. So we'll do the square root of x plus h minus the square root of x over h. So what do you think I should do to rationalize the numerator? What do you want to multiply by?
Square root of x plus h plus square root of x.
Beautiful. So we're pretty used to multiplying by something to change the denominator into what we want. But if we want to change the numerator into something, we can use the exact same process. Just multiplying by whatever we need to make the numerator do what we want. And then, of course, multiplying it by the same thing in the denominator. So since we're rationalizing the numerator, I'm going to distribute in the numerator like I did in the denominator before, and I'm going to leave my denominator factored, right? Because it's a product, so I might be able to cancel something. So we have h times the square root of x plus h plus the square root of x in the denominator. And then in my numerator, it looks pretty messy, but we'll just follow through and trust that it's going to work out nicely. So the square root of x plus h times the square root of x plus h, well, that's just the same as squaring it, right? Multiplying it by itself. So we have the square root of x plus h squared. And then we're going to do the square root of x plus h times the square root of x. And I'm just going to write that, like I'm not even going to worry about what that becomes, because hopefully it's going to end up going away anyway, right? Those two middle terms we want to add to 0. So rather than trying to figure out what that looks like as one radical, I'm just writing the product because I think it's going to go away anyway. Make this longer here. And so now we're distributing that negative root x. So I have negative root x times the square root of x plus h. And then negative root x times root x. So minus square root of x squared. And so as ugly as that is, I do notice that the middle two terms add to 0. So that makes it better already. And then what's the square root of x plus h squared? Yeah, it's just x plus h. And then the square root of x squared is just x. And we'll leave our denominator the same. And then I've got x minus x, which gives me 0. So my numerator is just h. Which ends up canceling. So what do I end up with in the numerator? Yeah, just 1. Remember that when we cancel that h, we're really doing like division, right? H divided by h is 1. So the only way to get a 0 would be doing addition or subtraction. So we always end up with a 1 when everything cancels there. And then square root of x plus h plus the square root of x. Anybody know what we just did? Is this recognizable or familiar in any way? It's the difference quotient of the square root function, right? If I had the function root x, then that will be f of x plus h minus f of x over h. So this is actually the place, like the one thing I can think of that you will definitely do if you're taking calculus of any kind, where you'll have to rationalize something. And it turns out here you have to rationalize the numerator and not the denominator. And the reason we do that is because, remember, with the difference quotient, we always want to cancel that h off. And so this allows me to simplify in such a way that I'll have a factor of h in the numerator that'll cancel the 1 from the denominator. So there's nothing really that special about rationalizing the denominator. It's just a process that I can apply to the denominator or the numerator to kind of achieve what I want. And so in different contexts, you'll find that it's appropriate to not rationalize at all, or it's appropriate to rationalize in the numerator or in the denominator. So we're really just gaining a tool that helps us to rationalize whatever the heck we want. Again, the difference quotient is just part of the definition of the derivative. So that's where you're going to see this. And you'll do this exact same process when you do the derivative of the square root function. So at least you've seen it once before. You guys ready to solve some equations? You feel good about this? So we're going to solve some radical equations. So when it comes to solving equations, like we have sort of our two standard equations that we know how to solve. We can solve linear equations by getting all the terms with the variable on one side and all the constants on the other. And then we can solve polynomial equations by getting 0 on one side and then factoring the other side. For all other equations, we sort of want to undo something. so that we end up with a linear or polynomial equation. Just like we did with rational equations, right? We cleared the fractions, and then all of a sudden we were back in the situation where we could either solve linear or polynomial. So the same is going to be true with radical equations. If I have a radical in an equation, I want to somehow get rid of that radical so that I end up with a linear or polynomial equation. So we're going to use a property that says that if A is equal to B, then A squared is equal to B squared, which basically just says I can square both sides of an equation, which is helpful because squaring a radical undoes the square root, right? So let's say we want to solve the square root of x equals 3. Well, I see that square root, and I want to undo it. So I have to square the square root of x to get x. And if I do it on the left side, I have to do the same thing on the right side. So we're going to square the left side, and we're going to square the right side, and we end up with x equals 9. And we notice that indeed the square root of 9 is equal to 3, so that works. So let's try this one instead. What if I wanted to solve the square root of x equals negative 3? So I could do the same thing, right? I can square both sides. Square root of x squared equals negative 3 squared. Again, here, parentheses are really important. When you square both sides of an equation, put the entire left side in parentheses and square it, the entire right side in parentheses and square it. We can't square things like term by term, like when we multiply. It has to be the entire thing. So on the left, we end up with x, and on the right, we end up with 9. But this time, notice when I plug that 9 back in, I get the square root of 9 equals negative 3. But what's the square root of 9? Yeah, it's just 3, right? And so that's not true. So what we did to solve this was correct, but we ended up with a solution that doesn't actually work. So we're back in another situation where we have extraneous solutions, just like when we solved rational equations. Because of that restriction on division, we couldn't end up with any x value that made a denominator 0. Well, same thing here. Because there's a restriction on square roots, we can't end up with anything that's going to make my square root equal to a negative. Because, do you guys remember how we defined a radical symbol? It's in Thursday's notes. So when we defined a square root, we found that every positive number has 2 square roots, right? Which was problematic because we wanted a function. And so we came up with this radical symbol, and how do we define it?
Absolute value.
So you're thinking of the square root of x squared was the absolute value, but you're on the right track with making stuff positive. Yes. That is also true, but it's not the definition of that radical symbol. That's a true statement for sure. So if you look at Thursday's notes at the very, very beginning, we said every positive number has 2 square roots, a negative square root and a principal square root. And then we came up with this radical symbol, and we said the radical symbol is always what? Yeah, it's always the principal square root. And that's what allowed us to get a single output instead of getting 2 square roots. So this is the principal square root of x, which means that the left side of that equation is always what kind of number? Yes. If that radical symbol represents the principal square root, it is always a positive number. So the left side is positive. Well, and -3 is negative. And what can we say about an equation that says a positive equals a negative? Yeah, it's just not true. A positive is never going to be equal to a negative, right? So as soon as I see a radical equals a negative number, I don't even have to do any of this. Eraser is not big enough. Okay. As soon as I see that, I can say this equation has no solution. So that's always something we're going to check for. If I have a radical on one side of the equation, the other side of the equation cannot be a negative number, which means I can't get any x values or solutions that make that other side of the equation a negative number. So let's solve a couple more. So the first step to solving any radical equation is making sure that there's only one term on that side. So let's do 6. So the only term I want on the left side of the equation is the radical term. And the reason for that, again, is that you can't square term by term because exponents don't distribute over addition, right? And so if I was going to square both sides of the equation as is, I would have to go like this. And we just saw when we were rationalizing denominators, this 2 isn't really working out for me. There we go. We just saw when we were rationalizing denominators that if I multiply the square root of x plus 4 by itself, I end up with radicals in those middle two terms, right? And so squaring both sides in this context doesn't get rid of my radical because I end up with one in those middle terms. So we always want to isolate the term that contains the radical. So we can subtract 4 from both sides to get the square root of x is equal to 2. And now when I square the left side, I'm definitely going to get rid of the radical. I'm not going to create any new terms with radicals. So I'm going to square the left and square the right. And we get x equals 4. And to make sure that's a valid solution, we are going to look at the step right before we squared both sides, where we had a radical alone on one side, and check that the right side is positive. And in this case it is, no matter what, because the right side is just a positive 2. So we have positive equals positive, which means there's no problems with extraneous solutions. So let's do another. Let's solve. We'll do the square root of x plus 7 plus 5 equals x. What should I do first? Anna, what do you want to do first?
Subtract the 5.
Yeah, we'll subtract the 5 from both sides so that the only term I have is the one that contains the radical. So we have the square root of x plus 7 equals x minus 5. And then Jess, what do you want to do next?
Can you square both sides?
Yep. So it doesn't matter what's under the radical. It could be like a huge expression. As long as the only thing on the left side is that radical, we can square both sides to undo it. So we've got the square root of x plus 7 squared equals, and remember, we square the entire right side. So what's the square root of x plus 7 squared? Yeah, it's just x plus 7, right? That exponent of 2 and the radical undo each other. So we have x plus 7. And then remember, when we square a binomial, we have to multiply it by itself. So we have x minus 5 times x minus 5. So x plus 7 equals x squared minus 10x plus 25. And then what should I do next? What type of equation is this? Nina, what do you think? Oh, what, where, who? Go ahead. Yeah, it's a polynomial equation. So I'm going to get 0 on one side so that I can factor the other side. So we'll subtract x from both sides. And we'll subtract 7 from both sides. And then we can factor the right side. So we have 0 equals x minus 9 times x minus 2, which gives me x equals 9 and x equals 2. Well, now I need to check to make sure those work. So what I'm looking for, again, is I want to make sure that if I have a radical on the left side of the equation, the right side is a positive number. So you look for the step right before you square both sides. It has to be before we square both sides, because squaring both sides is what creates extraneous solutions. So I have a radical alone on the left side, which means the left side of this equation is positive, no matter what. And so all I want to know is when I plug my x values in, if that makes the right side positive or negative. If it makes it positive, we're good. If it makes it negative, then it's not a valid solution. So when I plug 9 in, is that okay? Yeah, plugging 9 into the right side gives me a positive on the right side, so I have positive equals positive, so that one's good. If I plug 2 in, that gives me a negative 3 on the right, so that is not a valid solution because it creates a contradiction. It creates a positive equals a negative. So one thing that you might notice is when I solve equations, like when I get to that step that has the arrow next to it, I don't cover that step up. Like when I square both sides, I don't go like this. I actually like wrote another step. Do you see what I mean? And the reason that I always do that, it's tempting when you have like your original problem to just be like, oh, I'm going to square both sides. However, if you do that, you cover up the step that you're checking in. So like if I was given, whoops. If I was given this problem originally, when I square both sides, it's tempting to just go like this. But you cover up that step that you're going to check in later with some exponents. And so that's why I always, from there, just write a separate step where we square both sides so that you don't lose where you're going to check your answer later on. So I'm not just making you write more, because, I mean, it'll actually help you check your answers, I promise. So I think we have time for one more of these guys. Let's solve um, 3 times the square root of x equals x. So on the left side, my radical is not alone. However, there's only one term. So remember, we weren't saying that we necessarily have to get the radical all by itself. We just have to get the term containing the radical all by itself. So from here, I could divide by 3 on both sides if I want, but then I have a fraction, and that's no fun. So from here, I'm going to square both sides. And that doesn't mess up my getting rid of the radical, because I'm not creating more terms, right? When we square a product, we can just square each factor individually. So this is 3 squared times the square root of x squared. So we get 9 times x, because the square root of x squared is just x, equals x squared. What should I do next?
Subtract 9x from both sides.
Yeah, we're going to subtract 9x from both sides. Because of that exponent, I know I need to get a 0. And then factor out an x. So we get x equals 0 and x equals 9. Because we set each of those factors equal to 0. And so now I want to check, and again, we go to the step right before we squared both sides. If I plug 0 in, do I get a positive equals a negative? No, 0 is okay because it's neither positive nor negative, right? The square root of 0 is just 0. So if you get 0 on one side, that's totally okay. You just can't have a negative on that right side. So 0 works. What about 9? 9's okay also, right? Because the right side is just x, so 9 is positive, so I get a positive on the right side if I plug in 9. So both of these are valid solutions. So tonight, you are going to add page 398, numbers 22 and 26 to your written homework. Those are just the 2 problems we didn't do last night from yesterday's homework. I think I got the numbers right. Yes. So those are just the 2 problems that we left off of last night's homework. So you're just going to do those in addition to the written homework that's listed.